beautiful and very easy, and I'm told by the speakers that this week will be even more easy than the last week's. And we'll do all we can to make you understand these beautiful topics. By the way, there are notes. If anybody still need a copy, please come and they're there. Okay, so today is an introduction to a series of 9 lectures which Jingli Chai and I are going to give. And let me tell you what we want to do. The basic thing, the basic idea we want to convey, the basic material we want to discuss is geometry of the moduli space of abelian varieties, but in characteristic P. So this is a variety, this is a scheme, or whatever you like. There are many components, so it's not a variety actually. And we like to discuss certain aspects of geometry of this space. And of course, as always with moduli spaces, it has the big advantage that points really correspond to a geometric object, that properties of the geometric object classify certain sets of points, and so on and so on and so on. Right? So you can lay your hands on a lot of subsets of moduli space by studying geometry. Now, you may feel very uneasy if you're completely characteristic zero minded, and you may think these poor people working in characteristic P, they have almost no methods available because they have no paths, they have no integrals to write down, they have no complex topology, they have no analytic parameterizations, and so on and so on. But Jingli Chai and I want to convince you of the opposite. Namely, in characteristic P, we have a lot of techniques available which are completely non-existing in characteristic zero. So we would be extremely pleased if you agree at the end of our 9 lectures that you have seen at least 1 or 2 new techniques not available in characteristic zero, but all over the place in characteristic P. In our lectures, we'll prove 2 theorems, and we try to give complete proofs, except that certain tools will be labeled by BB, which means black box. So we have tried to arrange the material in such a way that certain methods, techniques, statements, facts are just too much to explain as far as the proof goes, but we have to explain to you the statement. So these are black boxes, and perhaps we should write SBB or LBB for small black boxes and large black boxes. Some are larger than others. And then I hope you are convinced that once we have announced the black boxes, that the proof really goes on. So let me first make a remark on notation. We'll write A and B and C for abelian varieties. We write X and Y and Z for P-divisible groups. And we write script A for moduli spaces. So please, if I write an A, make sure that I do the right thing in really distinguishing the abelian variety or the abelian scheme, and this for the moduli schemes, moduli spaces. Now, in order to make at least one more remark on the way the course is set up, we have arranged as follows. The first lecture is just an introduction, exposing to you what theorems we're going to do, put everything in the framework, giving some of the basic definitions. Then the last 2 theorems, the last 2 lectures on Friday, we'll prove the 2 theorems. And in the days in between, we have 6 lectures, and each lecture consists of a discussion of one basic tool. So that disguises our idea. The theorems perhaps are not so very important, and I hope after the lectures you will say, well, come on, the theorems, okay, they're nice, but who cares? But the techniques, the tools, they're really very interesting. So the middle 6 lectures, each lecture gives you one tool, one theorem, and I hope you can enjoy those as discussion of new tools, as discussion of really theorems, as things you can use. Now let me make one more remark, which is, I think, quite essential for understanding these basic techniques. So, philosophical remark, suppose you have a field in characteristic 0, and let's take the algebraic closure. For small k, I always mean an algebraically closed field. And let A, B, and B be abelian varieties over K. A and B are abelian varieties, right? And then you can form, for any integer, you can form the kernel by n. Square brackets, integer on an abelian group or abelian group object is always the kernel by multiplication by n, right? And then these two are isomorphic. If you work over K. And now you know, and I don't need to tell you, how to distinguish AN and BN. It's just a Galois action on both. And well, the whole theory of Wiles and of everybody else on elliptic curves really is associated with that Galois representation, right? However, be careful. If K, now let's immediately go to an algebraically closed field. If K is characteristic P, and you study for all A, abelian variety, say of dimension fixed, you study the set of isomorphism classes of P square kernels. So I take these for all abelian varieties A of dimension G up to isomorphism over K. And the fact is that this number of isomorphism classes is infinite, say for G bigger than 1. So all of a sudden there is a new technique, namely if you have an abelian variety, you have the kernel by multiplication by P, you have the kernel by multiplication by P squared, you have all these kernels and you can put them together, and that gives you a completely new set of invariants. Sometimes invariants are finite in a finite set, sometimes they're an infinite set, and so on and so on. Okay, so these are the few warning things I want to tell you. Now let me give you first a theorem. One of the two theorems we're going to prove is the following. So this theorem was proved by Ching-Li Chai in 1995. And I'll discuss the statement of the theorem and the things you will see in this. Okay, so I have to explain you what script H is, what script HL is. I have to explain you what ordinary is. Whenever I say dense, I really mean Zariski dense, and I omit the word Zariski. And I hope you agree that I don't discuss anymore the definition of moduli spaces. So I assume that you know what the modular space of abelian varieties is. You know you can define this LMM-Mumford over Z, and then you can reduce mod P, and that's a very interesting object, and that's the main animal in our zoo which we're going to introduce to you. Okay, so now I have to introduce you a few concepts which are here. First of all, let me make a remark. It's not in the notes, but it's easy, and you will. The condensed remark you can prove as an exercise after Ching Li has discussed the DNA modules with you. Suppose N is a finite group scheme over a field algebraically closed in characteristic P. Now, I didn't say commutative, but with the conditions below, it automatically is commutative. But let's assume all group schemes considered are commutative, so that word is certainly suppressed. And suppose that the rank of N is P. So what does this mean? N is an affine scheme, so it's a spectrum of a ring. This ring is an algebra over K, and by rank of N equals P, you just mean that the dimension of that K vector space, the rank of this algebra, is P, where P is the same P as P, right? And then we claim that N up to isomorphism just is in one of the following three boxes. Mind, the field is algebraically closed. Either this is isomorphic to mu P, which by definition is to take the multiplicative linear group and you take the Frobenius kernel. Or it's isomorphic to alpha P, which by definition is the additive linear group Frobenius kernel. Or it is Z mod P underlined K, where we have the following convention. If you have any group and you underline with a scheme, that means you take the constant group scheme with this group. So if you want algebra, you take all maps of Z mod P into K. That's the natural way in algebra, and it becomes a co-algebra by the addition on G, and taking the spectrum of that just gives you a constant group scheme. So all fibers are isomorphic to ZP. I have to make one apology and I have to make one remark. If you write a Abelian variety over a field, we really mean a Abelian variety over that field. And if we base change, we have to indicate. So if you have an Abelian variety over K, and we write the endomorphisms of A, we really do mean the endomorphisms over K. And that's completely different from what usual people on elliptic curves are doing. I mean, people on elliptic curves have no shame to write an elliptic curve over Q. Then it says it's had complex multiplication, meaning that if you go to the complex numbers, it does have more multiplication. Then write E square brackets FP, meaning the FP points and so on and so on. But certainly we will not do that. I mean, we follow Grothendieck in the sense that we are extremely precise. But please allow us an exception. The mu P is defined over FP, but we write mu P without indicating over which base. So taking the endomorphism of alpha P doesn't make sense. And yeah, and the same for alpha P. So we should write here comma spec K, comma spec K. And then every time we should indicate over which base field we're working, but we don't do that for mu P and alpha P. Okay, now there are many ways of defining what is an ordinary Abelian variety. And in the notes I've written some statements on P ranks and so on and so on. But please allow me to write the definition in a very short way. a beam variety over a field. By the way, from now on, all base fields have characteristic P, except for one little exercise. But this certainly is characteristic P. We say that A is ordinary if you take the hum of alpha P into A, and as this alpha P, that this is 0. And equivalently, this says that if you take A, you take the kernel by P, and you take the values in an algebraically closed field, that this is isomorphic to Z mod P to the power dimension of A. And this is equivalent by saying that if you take the Frobenius kernel on A and you tensor with K, this is isomorphic to mu P to the power dimension A. So either one of these is okay. And I hope you will feel the following structure. Namely, if you have in the beam variety, it gets more interesting if the alpha P in A is not only 0 humming into it, but the ones which are ordinary, they should be the most general ones, and actually we can prove that. It's not an easy theorem. And in general, but that's certainly a philosophical statement which I have to make much more precise, ordinary beam varieties behave, quotation marks, exactly as the beam varieties in characteristic 0, in the sense that all group schemes of a given rank are finite, all subgroup schemes are of a given rank are finite in number, Hecke correspondences are finite to finite on the ordinary locus, and so on and so on. All things which you're accustomed to in characteristic 0, except of course for analytic parameterization. However, if the beam variety is not ordinary, all these things tend to be slightly non-true. Bill, can I erase your statement? Okay, now in the notes you will find an extensive way of describing Hecke orbits. You know why I'm doing this? If you've ever given a concert in open air, putting your music on your stand, and then after the first wind you don't see any notes anymore. So that's why I put my I put a clap on my paper here. Okay, so now I define your Hecke orbit. So I'm now with you in the remark in the middle of page 4. And I start with a point. So I take a beam variety, I take a polarization on it, and square bracket means its moduli point in the moduli space. So A is in the beam variety, lambda is a polarization, brackets means you take the pair, the parenthesis, the square brackets means you take the moduli point. And I'm going to define for you when another point, or perhaps the same point, is in the Hecke orbit of X. And there are many definitions of it, but we thought it would be nice to start with the simplest definition. So we do the following. Suppose that Y is the moduli point of B mu. Now this concept is equivalent by saying there exists a diagram B mu, yeah, Yeah, I call that psi, I guess, yes. Where mind, by this notation, I mean there is an isogeny from C to B. You can pull back by this isogeny the polarization, and this is equal to zeta. Okay, so this is the definition of a Hecke orbit. So if you want to have a notion of it, you say, when is B in the Hecke orbit of A if it is quasi-isogynous to A? Mind that if I have this C and I go down to B, of course you can find an integer and have a commutative diagram like this. So up to multiplication, up to dividing by an integer n, this is isogynous to this. Right? So you may attach your philosophy to this is true if and only if B is isogynous to A. Now that's not quite true. We have to be careful on the polarizations. So we drag along the polarizations. Okay, now I've defined for you all notions. And I have one more notion to explain to you. Suppose that the degree of lambda equals the degree of mu. Yeah? We say that y is in the Hecke L orbit of x. L in the whole course is a prime number different from P, right? If the degree of phi is some power of L, is the degree of psi. Now in the notes you will find more extensive notion on prime to P and Hecke L and so on and so on. And please read these notes and the definitions and translate all the more general definitions into these. Okay, now the theorem we want to prove is the following. You take a moduli point, but in the course we only discuss the case where A is ordinary. You take the Hecke L orbit of that point, and here G is at least 1. Then the claim is that the Hecke orbit, the Hecke L orbit of that point, is dense in the principally polarized case. You see, you should be a little bit careful if you go up a degree of the polarization, right? It might be that you have to introduce not only powers of L, but other powers to get the correct degree. So that's the only reason we write principally polarized here. And hence you will see that the Hecke orbit is dense in AG. Now, Jing-Li Chai proved this theorem in Inventiones 1995. You will find this beautiful theorem. And on the course on Friday, Jing-Li will finally prove this theorem. But the proof is different from the 95 Inventiones paper. Namely, the reason is the following. We were working on this and we thought, why do we take ordinary beam varieties? Is it really necessary to do this for ordinary beam varieties? Now, let me note, and that's an exercise which is in 1.5. Suppose that an elliptic curve is supersingular, which by definition is the same, it's not ordinary. So if you want, it has no physical points of order, exact order p. It has not mu p in it. The Frobenius kernel is isomorphic to alpha p. All these are equivalent statements. And let's try to form the Hecke orbit. And you take some polarization on it, and you know all polarizations are about the same. And you take the full Hecke orbit, or the L Hecke orbit, or prime to p Hecke orbit, doesn't matter so much. And say you intersect this with AG1, A11, which of course is the affine line. Yeah. Yes, thank you. Yeah, that was one of my remarks. I always tend to write smaller and smaller, so I have a spy in the in the background. Thank you very much, Ronald. And please notify me. So this is Hecke orbit of X, and I intersected is the principally polarized. And the question, is this dense? And the answer is, of course, no. Because supersingular elliptic curves are only finitely many. And whatever you do under isogenies, it stays supersingular. So whatever this Hecke orbit is really doing for you, it moves in this finite set. So you only get a finite set. So the answer is definitely no. But as I observed talking with Chengdi in the 90s, I observed a way of proving the following theorem. I will define for you what is a Newton polygon. So script n is a Newton polygon, and I will define that for you. And every Newton polygon defines a stratum. So for elliptic curves, the ordinary stratum is everything, and the supersingular stratum is just this finite set of points. And that we're going to generalize. And in the 90s, I made a conjecture that the Hecke orbit, in fact, is dense in this smaller set. And that now has been proved. And in order to prove this theorem, we needed several notions. And the bonus is that in proving this theorem, we came across a lot of new techniques. And these new techniques will go into the proof of the ordinary case, which becomes, we hope, much more transparent. Okay. Are there any questions so far? Should I explain more? Okay, so this is the thing we're going to prove for you. That's one of the two theorems. And the other theorem is the following. In 1970, Grothendieck gave a course in Montreal, and he had a conjecture, and so that's called a conjecture by Grothendieck, but in this course there will only be one, so in this course we'll call the Grothendieck conjecture. And let me read first the theorem for you, because that's the theorem we're going to prove, and then I'll explain the words in the theorem. We take only fields and base schemes in characteristic P. And we have a P-divisible group, and I'll explain what it is. And to a P-divisible group, you can associate a Newton polygon, beta. And such Newton polygons have a partial ordering, saying that beta is smaller than gamma if it is above gamma. Some people always get very mad at me with this notation because it seems that the lower ones are the smaller ones, but the upper ones are the smaller ones. And the reason is that if you take Newton polygon strata, the more the Newton polygon goes up, the smaller the stratum becomes. So this smaller really is the same as smaller in the geometric sense. Okay, so we have a Newton polygon. And we have given two data. The first is the x0, and the second is gamma. Now, Grothendieck in his Montreal notes explains that if you specialize p-divisible group, the Newton polygon goes up. And Grothendieck asks, and the concrete text is in our notes, is the converse true? So if you find two Newton polygons, can you realize these two Newton polygons, the lower one as a generic fiber Newton polygon and the smaller one and the upper one as a closed fiber one? Now this I call the weak Grothendieck conjecture, that any two Newton polygons ordered this way can be realized in a family, but the Grothendieck conjecture asks for much more. Namely, not only that beta lying above gamma is realized, but that you realize it really with a given closed fiber. And I'll show you in this course that the weak Grothendieck conjecture is not so difficult. But the true Grothendieck conjecture, where you beforehand give the closed fiber, that's a much harder theorem. Okay, so the theorem says I take a p-divisible group, I take a Newton polygon below its Newton polygon.
Franz, is there a conjecture when the slopes are between 0 and 1? Say slopes between 0 and 75?
Strictly, you mean? There may be.
I mean, I don't remember either in conversations or in something I saw written by Grothendieck, him formulating such a conjecture.
Oh, sure, it is in the Montreal notes. And
no,
well,
no, certainly this is, it's in his letter to Bassadi, in those notes, but I'm asking about when you take things that don't correspond to each one.
I don't know. No. All our slopes are between 0 and 1. So does that answer your question?
Yes, but I was asking, is there some more general conjecture that slopes between 0 and...
I've never seen it, and I don't know whether it's true or not. But if you want, we can discuss. Certainly I need this condition. So our Newton polygons are not Newton polygons of some crystal, but really of a p-divisible group. Thank you for your question. Okay, so we have given x0, we've given gamma, and now the result is that there does exist a p-divisible group over an integral base in characteristic p, a k point on it, such that if you take the fiber of your p-divisible group over your whole base at 0, it is the given one, and if you take the fiber at the generic point and you take its Newton polygon, it is the gamma you want. Right? So this is the theorem, and we're going to prove this theorem. Now, let me explain a few of the notions. That I'll do for the next 10 minutes, and then the last 15 minutes I will at least prove one theorem. So, definition of a p-divisible group. Where is it in my notes? 118. I'm going to define for you a p-divisible group Actually, I should say a p-divisible group scheme, and some other people say Bassadi-Tate group. Or Bassadi-Tate group scheme. So, let me stick to my notation. Notation we have in the notes. So this is over any base, and mind the base now need not to be in characteristic P. This you can do a mixed characteristic, you can do in characteristic 0, or whatever you like. So this is over spec Z. And suppose we are given a number which certainly I won't call H. And suppose we have Gi over S, finite flat group schemes, mind are commutative, and such that the rank of Gi over S is P to the IH. And moreover, we have inclusion maps for any J bigger I, and we have it in such a way that Gi is exactly the kernel of P to the I on G to the J. And then you can form the inductive limit of the Gi following these maps, which of course you should consider as you should feel like the union of the Gi, and this is a p-divisible group. And of course the basic example is if A is an abelian scheme, then you just define Gi to be a kernel P to the I, right? And this defines you X, which is Gi. Now, I would like to have a little discussion for you. You know, if I take a prime number L in any characteristic, but certainly not equal to the characteristic, you can form the theta L group of A. And how do you do it? You take A L to the I, right? And now you take the inverse limit under multiplication by L. So A Li plus 1 to A Li, this is multiplication by L. And for some historical reason, but also for some minor technical points, here we have the inverse limit, and in the p-divisible group we have the direct limit. But that doesn't matter, and that shouldn't bother you. I mean, you can as well take here the direct limit and there the inverse limit, and, well, you have to rephrase theorems to be a little bit more careful, but that's not the point. So please don't mind the direction of the arrows. But please do mind the difference between this and p-divisible, where p is the characteristic. Namely, you should feel the following. These are, of course, important objects, and they're completely algebraic objects in the sense that if you go to the algebraic closure, this is just ZL to a certain power. And if you don't go to the algebraic closure, you have a Galois group operating, and in the notes we have explained how from that general picture with the Galois action you can recover the original one, and from the original one you can set up the Galois action and so on and so on. So I should stress that this really is an algebraic object. It feels like a cohomology group, and in fact it is a cohomology group, but you should feel it as an algebraic object. But mind, a p-divisible group is slightly different. So a p-divisible group, first you can go to the algebraic closure. But as I explained to you already, if you take kernel by p square, there are infinitely many isomorphism classes. So a p-divisible group is something which is not pure algebra. but it's in between algebra and geometry. We really do have moduli spaces of these. And actually one of my lectures, the complete lecture will be devoted to a certain moduli space of p-divisible groups, writing down for you the definition, proving the moduli space exists, is irreducible, and so on and so on and so on. And that will be the key for proving the Rodney conjecture. So this you should feel partly as a geometric object. Now you may wonder, what remains of the fact that here we have an algebraic object plus Galois action determining everything. Now here we have three aspects. One aspect is we have moduli. Really, they really can change. The second is that we have a Galois action. If you first go to the perfection of your field and then to the algebraic closure, this Galois group operates. But then there's a third, and that's extremely useful, important, and beautiful, the difference between your field and the perfection. And the whole theory of Serre-Tate coordinates, which Ching Li will explain you, rests on the fact that if you take a p-divisible group and then go to the perfection, it completely changes in nature. So a p-divisible group has three aspects. First of all, it has a geometric object. It really has moduli. Second, it has Galois theory. And third, it has what I call, bad word, inseparable Galois theory. And these three aspects, you think difficult, but they're not difficult at all, and they give a rich structure on these. Okay, so that's what, so far as I'm going to say something about p-divisible groups. Now, I want to explain something which is the Newton Polygon. Now, certainly, in a short lecture, it's impossible to explain completely what a Newton Polygon is, so we have two layers of understanding. Today I'll explain you in 3 minutes what a Newton Polygon is. Then you should know. And then to give the correct definition, we need much more technique. Okay, so here's the bad definition, and the bad definition is in my notes. Yes, that's page 9. And it's the heading which says incorrect. So now I give you a completely incorrect definition, and one shouldn't do that for mathematicians. So let's close the doors, and you don't tell anybody. But then afterwards we have had your name modules, you know the correct definition, right? You have a p-divisible group, X. So that's a p-divisible group over a field. And we take the Frobenius endomorphism. And I'll put quotation marks later to warn you that it's nonsense what I'm saying. This Frobenius endomorphism of X has a characteristic polynomial right? And this characteristic polynomial, you can take its Newton polygon. So what's a Newton polygon? You do the following. This characteristic polynomial is something like, I have a notation for it, so let me adhere to this notation. Gamma j t to the h minus j. So let this characteristic polynomial be this. Yes? And then what we do, on the j's place, we take the p-adic valuation of gamma j. Now, because your Newton polygon, because your characteristic polynomial is monic, the VP of gamma 0 is the top term. So here the VP of gamma 0 is 0. And here it is something. And so you have certain sets of points. You take j and you take this is coordinate, and then you take the lower convex hull. So this is here, this is here. So this is the lower convex hull. Now it's an easy exercise, and if you've never seen this, I think you should spend at least 5 minutes of your week here to prove the following theorem. It is in the notes. Suppose you have a polynomial over a p-adic field, and you want to find the zeros in the algebraic closure and then the p-adic values of these zeros. Claim these p-adic values can be exactly gotten by the slopes of this Newton polygon. And of course it's easy because the constant term is the product of all the zeros. The one but non-constant term, the linear term, is products of h minus 1, products of these, and so on and so on. So that immediately proves this thing. So what does this Newton polygon gives you? It gives you immediately the p-adic values of f as slopes. Okay, so
The normalization is that p has value
1. Yes, yes. So these are rational integers, right? And if your polynomial is over QP, it's a miracle that these slopes are just rational numbers, but that these are integers. Okay, now why is this wrong? This is completely wrong, this explanation. Because what does f does? F maps x to xp. So it's not at all an endomorphism. It is an endomorphism if you're over the prime field. So my explanation is correct if I work over the prime field, right? Now, what do I mean by characteristic polynomial? That's also not so easy. So this explanation certainly is not a definition, but please take for granted that we are going to give you a whole set of techniques which allows you to start as a p-divisible group, then develop a notion of eigenvalues of Frobenius, then develop a notion of p-adic values of these eigenvalues. That gives you a set of slopes. These will order an increase in non-decreasing order, and that gives you a Newton polygon. So a Newton polygon, now I should give a formal definition. It starts at 0, 0. It ends at h, c. H is here. C is here. It is in polygon, and the breakpoints are in Z cross Z. Okay, so now you know that there are a finite number of Newton polygons as soon as I've given you H and C, because there are a finite number of breakpoints possible. And sorry, plus lower convex. Okay?
So h is the height of p-divisible?
Yes, and h is the same h which I've given you. C, yeah. The dimension of x we usually call d, and h is d plus c. So c is what they call the codimension. Okay, so that is that's the Rodney conjecture. Now, I want to. I'm sorry, I'm hiding this board because I need space. I want to at least prove one result and then announce you the Manning conjecture. So now I go with you to where is it? To 110. I backtrack in my notes and I go to 110. After all, we have to connect our things with its being varieties. So, first technique is for n, which is a finite flat group scheme over any base. We can associate its Cartier dual. So what is it? N is finite flat. So n is a spectrum of an algebra. This algebra we can dualize as linear harms into the base ring. That gives you an algebra, because finite flat, gives you an algebra of the same rank. And the multiplication on the original algebra becomes a co-multiplication in the dual. And the co-multiplication in the original becomes a multiplication in the dual. So the spectrum of, this is the spectrum of what they call a bi-algebra. It is a ring, it's an algebra over the base ring, and it has a co-multiplication, a co-inverse, and a co-unit. Now the dual of that automatically has all the same data, only multiplication and co-multiplication are interchanged. Right? And that we call the Cartier dual. By the way, if you take this group scheme and you apply D by a Cartier dual, we get exactly the same object. And if you apply this one, and we get, well, actually, how we get this one. Now, from the definition, this is not completely easy to prove, but soon I'll announce you a theorem which really allows you. Then, suppose I have a p-divisible group. I want to define a dual of this. Now, some people denote this by x upper d, but that I don't like at all. And I'll define for you what we call the Serre dual. And it's the following. Suppose x is given by gi, right? Then what we can do is we can take gi Cartier dual, but mind, the arrows are reversing, right? And now, of course, we can have gi sitting into gi plus 1. We can dualize this. This is gi dual gi plus 1 dual, right? But now we can do the following trick. We have gi, gj, j is bigger, equal I, cj plus I, cj minus I. This we can Cartier dualize, cj minus I, cj, and we can take these maps for defining the Serre dual. So if you want, take gi plus 1 to gi and dualize as maps. And this is called the Serre dual of...
So are you going to say anything about why you have the exact sequence, or you assume that as a small black box?
There's a small... okay, small black box, you're right. These are finite and flat, that this is an inclusion, and then Grothendieck proves that this quotient does exist, and then you immediately prove that that quotient is included in gi minus 1, has the correct rank, and hence has to be equal. Okay, you're right. Small black box. You're right. Thank you, Bill. Okay, now I have the following theorem, which is called Duality Theorem. So that's 110, sorry. Suppose I have an isogeny of a being varieties. So phi is an isogeny over any base. Mixed factor, yeah. the Cartier dual of this, one,
The definition of existing.
I have GID, right? And now I must explain you how GI dual is mapped to GI dual. No, the dual is here and on the map. I have these objects, right? And I have to tell you how GID sits inside GI plus 1D. And then I take the union over such arrows, right? Now I claim that GI plus 1 maps onto GI, and that's a multiplication by P, if you like, right? Then I can dualize this sequence and get something like this. So all I want to say is this is an inductive limit over all inclusions. Then from that I can take projections by multiplying by powers of P, and that I can dualize. Yes? Is this? Okay. Thank you for your question. I should have made more explanation there. Okay?
For periods of group associated Wiener varieties, you get the same.
Well, I'll explain in a minute. Suppose I have a isogeny and let n be the kernel, right? Then I can dualize by just taking the Picard scheme. So AT is taking the Picard scheme, then connected component of the identity, and that again is in the being variety, right? And I can take the kernel of phi t, and my claim is that this is canonically isomorphic to the kernel of phi. And now Cartier dualized. Now let me first answer the question I just had, right? Corollary of this theorem is that if you take the being variety, now I can do two things. I can first take the p-divisible group, which I denote by p infinity, nonsense notation because p infinity doesn't exist. But this is just the union of all the p power kernel maps. And this I can Serre dualize, or I can take the being variety, then first dualize in a geometric sense, and then take its p-divisible group. And they're equal. Does that answer your question? Okay. Hmm? Oh, sorry. This is A. Thank you. Yeah, thank you. Okay. Now this looks obvious from notation, but it is non-trivial. I mean, the notation is just chosen in such a way. Now, why is this? You see, proof, apply duality theorem to A multiplication by P to the I, A P to the I. Yeah? Now, if you apply duality theorem, you get the same A dualized. You said to get the same A dualized, right? And the dual of multiplication by P to the I is just P to the I. So the kernel of the dual sequence is the Cartier dual of this, on the one hand. On the other hand, it is the P to the I kernel of AT. Okay, now I'll spend 1 minute to prove the theorem. And in the proof, I need two black boxes, which are not in the notes, but I'll explain. You take the following sequence. I take the hum of A into GM, hum of B into GM, hum of N into GM, And I'll explain then x1 of A GM, x1 B GM, and I could go on, but I don't want. Now, what are these underlined hams and x? These are, well, you have to do sheaves on some Grothendieck topology. What you do is...
X1 and GM is 0. So there's no point in going on.
No, I know, but I didn't write it yet. So, what is this ham? You take, over any base, you base change A to the new base, GM to the new base, and you take the homomorphisms of that to be in scheme to GM, right? And so for any base, you get a certain value of this functor. Now this gives you a sheaf on, say, some topology on the set of all schemes over your base scheme, and that sheaf is what is written here. Now it's clear that this is trivial, right? And for the same reason, this is trivial. So I can start at 0 here. And there's a formula which says that this really is representable by the dual. And that's isomorphic or canonical isomorphic. And that's what is called the Cartier-Schatz formula. So that's a black box. Right? Then we go on, and it turns out that this is just a T, isomorphic, and that's called the Weber-Soddy formula. And so this is BT, and then there are two ways to see that this is surjective. Either you know that this is an isogeny, so it's surjective, or as Bill explained to you, the X1 and GM is trivial, so the two ways to prove it is surjective. So the strange behavior of the theorem says that all of a sudden you have a three-term exact sequence here, and then you get the one part which is 0. So up to these two black boxes, right, the proof is obvious. Okay, now I want to make one more corollary and then I stop. So where do I write that corollary? As soon as we've seen the good definition of the Newton polygon, we see that the Newton polygon of A, and by this we mean the Newton polygon of the p-divisible group, right, is equal to the Newton polygon of the dual. And for this you really need some more insight in how to construct it. And hence, the Newton polygon psi is symmetric, by which we mean that if a slope beta appears, then in psi, then 1 minus beta appears in psi. So that gives you kind of feeling which Newton polygons for abelian varieties will show up. And soon I will discuss for you a conjecture by Urimanin, namely this was proven by Urimanin for abelian varieties over finite fields, and then he asks if conversely you take any symmetric Newton polygon, does it appear as a Newton polygon of abelian variety? And in my course I will give you two different proofs of that theorem, of that conjecture, and actually that has been proved now. Let me stress that Ching Li are willing to answer any questions, so if you have any questions during the week, please come to us and ask whatever you like. And I thank you for your attention today.